Good morning or afternoon, everybody. How are all of you today? Well, I don't answer because, I can't hear you because I'm not here. But hope you are all having a fantastic day. I am going to be recording my screen here using OBS Streamlabs. We'll see how this goes. I also have a digitizer and a pen that I have hooked up wirelessly, and a whiteboard app that will allow me to draw on the screen. So I want to go over a lot of the topics that I've been having you watch videos of and explain them in more depth. So let's go through some of them to start. For our first one, right, we had our chemical bonds, right? Types of chemical bonds. And actually, let me just see. I guarantee you there's some website out there, blankwhitescreen.com. This will work. So let's talk about chemical bonds. Right, I just started talking about this the day before, I had to leave and all that. But we have three. Let's go for a black. That'll be good. To use that. Well, who cares? Three types of chemical bonds. We have ionic, we have covalent, and we have metallic. So ionic, covalent, and metallic. I'm going to make this writing a little bit smaller. Sorry, guys. Let's go for 3 on that. Let's see how that goes. That's better. Alright, so ionic, covalent, and metallic. An ionic bond, right, is a bond which holds together, which is formed by positive and negative ions holding each other together. And what you get is an array of atoms. Imagine this going in every direction into the page, out of the page, right, into your screen, out of your screen, to the side, to the left, to the right, up and down, pretty much infinitely until the end of the molecule, or until the end of the compound, rather. There's not really a limit to how big these can be. I mean, after all, you can see, right, huge salt pillars. And these are essentially all connected chemically. Right, you can make an argument that that is one entire compound together. So these can be really tiny or they can be really big. It's just a matter of how often and how much it repeats. And I'll come back to covalent in a second. Then we have metallic. A metallic bond, right, is one that's formed from a... no, I want to say that. guess I'll just cross that out. Sorry, still figuring out how to use this. A sharing of electrons. No, sorry. That's covalent, sorry. A sea of electrons. That's what my brain was thinking, and then my hand just wrote something else, and I just read what I wrote. A sea of electrons. The important part is these electrons are delocalized. So a localized electron would be where you have an atom, right, with a nucleus in the middle, and the electrons stay within the electron cloud of that atom. In a delocalized electron means it can move around. But because all of them are delocalized, they're all kind of spread out evenly throughout the metal. And it's the electrons moving around evenly, being all over the place, that's actually holding it together. This is actually why metals are really good at conducting electricity, because you can run a potential that travels through these delocalized electrons that can move around. In addition, you can actually make one part of a metal more positive and more negative. You can put a charge, right, on one part of a, let's say a positive charge on one part of a metal that causes electrons to flow to that side. And actually, I believe, right, and that makes this part of it negative and it's part of it positive. You can actually cut it in half and end up with a fairly charged hunk of metal on either side. So just something to think about. They're literally delocalized. They can move freely, and most of the time they are evenly spread out. But we can manipulate that with electricity, which is actually really useful. That's how we make a lot of detectors for certain things. Then we come down to covalent. I'm going to clear the page now, so if anybody needs to, it looks like they need to get this down, you should stop and kind of take notes now. Because I want to talk about covalent on its own. Covalent is the sharing of electrons. Right. Valence shells from different atoms are shared to fully fill their shells. So for example, nitrogen has 5 valence electrons. Carbon has 4 valence electrons. They both want to reach 8. Carbon and nitrogen could form a single, double, or even triple bond for the sharing of, from each of them, 1 electrons, 2 electrons, or 3 electrons. Or in the case of cyanide, right, they do move the electrons around, and they kind of, they move them around to reach a shape. So even though carbon ends up with an extra 1, right, they both get 8. There are 2 types of covalent bonds, though. Right, we have polar and non-polar covalent bonds. Polar versus non-polar bonds are all about electronegativity. So, if one atom is significantly more electronegative than another atom, the bond is polar. An example of a polar bond is OH. And actually, if we take a second and we look at our periodic table, and we look at electronegativity, we can look and we can see oxygen has polarity of 3.44, while hydrogen is 2.20. Now, I believe the exact number is just a 0.5 difference. But let's check on that. because most of the time we won't really be looking at minor differences. Yes, it is 0.5. So, for a bond to be labeled as polar, most of the time, there has to be a greater than 0.5 difference in electronegativity. Right, so nitrogen and hydrogen, that's 0.8. Oxygen and hydrogen, that's 1.2. This is a polar bond. So, we can look at this and we can say, okay, this is polar. What does polar mean? Polar means we have a dipole. A dipole is where you have two poles with charges, and there's a difference in the strength of one of them. So the poles are each atom. Let's think of these as just spheres of influence where the electrons can be, right? Here's our two poles, and what we're looking at is how electrons go in between them. Oxygen is much more electronegative than hydrogen. That means it likes electrons more, and it takes them in more. So if this one is oxygen and this one is hydrogen, the electrons are going to be spending a lot more time near the oxygen. Imagine a bit of like an egg shape, right? Where the larger the size is, the more time is spent there. If you want to call it the density of the electrons. So most of the time, the electrons are near oxygen, even though they're technically being shared. This actually makes it really easy for hydrogen to break off, which is actually one of the reasons why OH is present in a lot of acids. For example, carboxylic acid, acetic acid, which is vinegar. It's present in a lot of acids because the electron spends so much time for oxygen. It doesn't have that much of a problem just breaking the bond and turning that into an ion, right, and making it a negative. Non-polar bonds are ones that are even. So either bonds that are made with the same exact atom or with similar electronegativities. So carbon and hydrogen is a classic example of a non-polar bond. That's only 0.35, not the 0.5 needed for polarity. And really, hydrogen and carbon don't pull that much. Yes, carbon pulls a little more than hydrogen, but not enough to really affect the strength of the bond or affect its properties. So things that have, right, all hydrogens attached to a carbon tend to be pretty stable and act the way you would expect. So these are non-polar bonds versus polar bonds. These can also then lead into polar and non-polar molecules, which I'll talk more about when we get into our portion with molecules and structures. So take a break from this. Let's look at what else we can talk about with our types of chemical bonds. Well, really, I wanted to go over some AP questions with these. So, I'm going to let myself draw on this page. We have a couple questions, and again, these aren't exactly AP questions themselves, but they're written by the people who make the AP questions. So, which of the following scientific claims about the bond in the molecular compound HF is most likely to be true? And we can look at these and we'll talk about why each of them is correct or incorrect. So let's read them all first. There is a partial negative charge on the H atom. Electrons are shared equally between H and F atoms. The bond is extremely weak. The bond is highly polar. So first, let's look at the periodic table. You do not need to memorize electronegativity. Instead, for polar things, they're going to give you things that are obviously polar right, which will be something strong from up in this corner. It will probably be nitrogen, oxygen, fluorine, or chlorine, maybe bromine. One of those will usually be combined with either carbon or hydrogen to show that polarity. Nitrogen and carbon are kind of right on that line of polarity, right? Technically that is 0.49. It's just about polar, but at the same time it's much more stable than a carbon-oxygen bond. So, you know, that's kind of the more polar than carbon-carbon, but not as polar as one of these ones. So, here we go. So, that is really what we're actually being asked about in this question. But let's think through each of these. A partial negative charge on the H atom. So here's what we mean by partial charges actually. We can look at these with polarity. We use these with a little delta to show a partial charge. A partial charge, right, is produced by something called a momentary dipole. Well, no, actually, sorry, is produced by a dipole, not a momentary dipole. I apologize. And the dipole being, again, the electrons are spending more time near fluorine. Fluorine is the most electronegative element. Hydrogen is middle of the road. It's not the least electronegative by a long shot. It's very middle of the road, but it's not nearly as electronegative as fluorine. However, hydrogen is the least electronegative element that you will commonly see in covalent bonds. So the electrons will spend some time near hydrogen, most of the time near fluorine, and some of the time it'll kind of be more like in between. But because fluorine is getting the electrons so much more often, it has a partial negative charge due to the electrons being there. And because hydrogen is more often than not lacking in the electrons, right? If this is a density chart of on average where they are, you're much more likely to find them near fluorine. And so we say hydrogen is more likely to be lacking in it, so it has a partial positive charge. So this is just false. There's not a partial negative charge, and for that to be true, right, it would need to be present, right, near, it would need to be present near, the electrons would need to be present near the hydrogen. Right, now we look into electrons are shared equally between H and F. Well, that's the whole point of a polar bond. They're not. They are not shared equally. So this one is just, and this actually is not true. HF bonds are very strong. But here's the other thing. We don't know which of the following scientific claims about the bond in the molecular compound HF is most likely to be true. We don't have any knowledge of that without measurement. And so this one just kind of is not the most likely to be true. It's something that maybe could be true, it could be plausible, but we don't have evidence of that just based on our knowledge alone. However, this last one, the bond is highly polar, our evidence of that is the most electronegative element with a much less electronegative element combined with it. So in this case, our answer would be D. All right, I got about another 20 minutes before this video is going to be over. So let's keep going. Talk about a few more concepts. Also, if the volume is not good, please send me an email letting me know. I want to make sure I get closer to the mic and talk more clearly going forward. This is an overall, kind of throughout the chapter question that I want to answer at the end of the chapter. So let's move on. This is an open response question kind of on the chapter as a whole, or the unit as a whole. So let's keep going. 3. One element is okay, a pure element reacts to form a compound. One element is an alkali metal X. Alkali is the first I need to choose sorry about that. Let me allow it to write on the page again, see if that'll work this time. Try this. So, alkali metal is the first column, the first family, our group 1. That means they form 1+ charges. We are told that an alkali metal is combined with a halogen. A halogen is a 1- charge. We are asked, right, to identify which of these things is most likely to be true. Which of the following is likely the most valid that we can make? So first off, from the formula with a 1+ and a 1-, this is just going to be false. It probably would dissolve in water. Most alkali metals do. It would not contain a covalent bond, because a covalent bond tends to be between two nonmetals. But by definition, an ionic bond tends to be one metal and one nonmetal, because metals are really good at forming positive ions, and nonmetals are really good at forming negative ions. So you would expect it to contain an ionic bond. And finally, we have the elements carbon and selenium have the same electronegativity value of 2.55. Which of the following claims about the compound that forms from carbon and selenium is most likely to be true? The bond is unstable. The bond is nonpolar covalent. It has an empirical formula of CSE. Or the molecule of the compound will have a partial negative charge on the carbon atom. Let's talk about each of them. The bond being unstable, we don't have any evidence for that in one way or another. So that's not going to be the most likely to be true. Same with the empirical formula. You would have to draw it out and come up with a molecular compound structure. We'd have to know how many carbons and how many selenium atoms we have to work with in drawing it. There could be multiple compounds formed with them. And then a molecule of the compound will have a partial negative charge on the carbon atom. Right, this one, again, this and B have to do with electronegativity. They have the same electronegativity value. If you had one that was more electronegative on the carbon, then you would expect a partial negative charge on the carbon. But they're exactly the same. And so we can say that the bond between them is non-polar covalent. It is not a dipole because the two sides are equal, so it's not being pulled from one side closer than the other, or more than the other. All right. We have about 20-25 minutes left, so let's talk about intermolecular force and potential energy. So the first video I had you watch talked about potential energy curves for covalent bonds. It talked about Coulomb's law with that, and then it also talked about ionic bonds with regards to Coulomb's law. I want to talk a little bit more about that and go a little more in depth. Now, potential energy curves are going to be something that you see quite a bit in this class. Right, a potential energy curve looks something like this. So some of you might have seen these and said, I don't really know what it's talking about. This is the energy. This is distance. Specifically, internuclear distance, the distance from the nucleus of one atom to the next. So you can think of this being the distance between how close and how far away two atoms, or how far away two atoms are from each other. If you have a distance that is too small, you get a serious overlapping, so let me overlap that even more, of atoms. And what you end up having is the electrons to some extent, but more importantly, the positive protons in each of them getting too close. The nucleus is getting too close and repelling each other. This makes for a very high energy. High energy is bad for stability. High energy, oh, do not pull up Facebook. High energy, right, means it is unstable. Energy likes to go to its lowest form, its lowest value. Right here, this is where it's stable. We call that a potential energy well. It's where things like to settle down because they don't like to be high in energy. Right? High energy means it has a lot of energy to react, and it will keep reacting until it has low energy. In fact, you want a negative energy to the point where what this means here is you actually have to put force in to break that bond. Right? You have to put in a certain amount of energy to break that bond. So, let's kind of talk about where each of these components is, or what each of these areas is on this chart. So this is our high energy, again due to, let me rewrite that into something that's not Zoetrosis. High energy due to these overlapping atoms. This is our low energy. This is our actual molecule. And that is where you will find any given bond on a molecule, right? Its most stable point. It's just enough distance that the nucleuses aren't repelling each other. But the electrons are still forming a bond together. For covalent bonds. And as we go further and further apart, they move away and the electrons hold, weakens, until it just becomes two separate atoms. And so the bond of the energy goes to zero. So as it gets further away, it approaches zero until it hits zero. And that point of zero is where it's just two separate atoms with no bond. This all comes down to Coulomb's law, that law I talked about the other day. So remember, before I left, force is proportional to, this sign means proportional to. All right, charge 1 times charge 2 over r squared. We'll ignore the k value because we're not going to do math with this. Instead, we're going to look at this concept. As the radius increases, right, this value goes up, and so the force decreases. That's why it goes to zero. When we are up here, though, we're no longer looking at an attractive force. This is an attractive force, right? The electrons binding the atoms together, and the electrons being shared between them are interacting with each of the protons in each atom, giving it stability, giving it an attractive force of opposite charges. However, right, when you bring them too close together, you get the repulsive forces, and so you have a low R, and then you start getting strong positive forces that are doing the interactions, and they are going to push each other away. But as you get away to this distance, these positive forces are no longer interacting each other, and the force for repelling really drops down, and then the force for the attraction is what is then taking center stage. So that's why you want to get right there. We can use the same exact formula for ionic bonds. I know we talked about this before, but if you have 2 plus and a 2 minus, they are going to have a stronger force because you have a greater charge versus a 1 plus and a 1 minus. Again, I know I've stated this before, but this is the reason why 1 plus and 1 minus charges tend to be soluble, and 2 plus and 2 minus charges tend to be non-soluble. When we look at these, one thing you will often be asked to do is compare these two, or is rather to compare two charts based on two different elements. Right? You will be asked to in fact, you need this bottom line, sorry. You'll be given one chart. In fact, let me... There we go. One chart and told it is based off one element. One of the most common ones to do this with is actually chlorine with other ones, and this is actually the example that's given in your problems for this chapter. Right, if we look at chlorine, and we're asked to compare a chart for bromine, and you might be asked to draw a second chart for bromine based on this one. Well, chlorine is smaller than bromine. We know this if we go to our periodic table, because bromine is one row down. If it's one row down, that means it has another energy level, and that means it has a larger orbital, and the larger orbitals are physically larger. It creates more space for the compound to exert. So then we have a greater radius. So again, we have our force is proportional to Q1 times Q2 over radius. So first off, what this means, if it's a larger molecule, then its lowest point is going to be further along in this distance. Right? Its minimum is not going to be here. It's going to be somewhere to the right of that. But it's also not going to be as high. It's going to be a weaker bond that's not as hard to break because of this force. If R goes up, the force of the bond goes down, and therefore the force required to break it goes down. So you're going to be looking at something like, let me change the color on this. Something like this, where it is both shifted to the right because it's physically further away, and at the same time higher up because it doesn't have as much energy. So let's talk about, oh, there actually were no problems for practice for that one, so I guess we can carry on, but that is a type of question you might get with that. Or again, you might just be asked to compare the strengths of bonds for ionic bonds as well. So if you were asked what is stronger, a magnesium oxide bond or a sodium chloride bond, you can answer that by referring to this, or just recognizing that for a multiple choice question. Saying, listen, this is a 1 plus and a 1 minus versus a 2 plus and a 2 minus. The hold on this is going to be a lot stronger. Even for something that's like a magnesium chloride, this is going to be weaker. You might look at this and think, oh, well, there's 2 pluses, and then there's 2 incidents of 1 minus here. But we have to think about what the structure is going to look like. You'll end up with a larger positive, and you'll probably end up with smaller negatives on either side. The Q between these is still going to be 2 and 1, and so it's still going to be easier to split that up. And then split that up, it's going to be easier to split up all the individual parts. But it is still stronger than a 1 plus 1 minus because you're doing a 2 times 1. And the exact force of Q isn't just going to be like 1 or 2, right? You'd have to look up the exact quantity of the charge really associated with these. And by that I mean the direct energy related to the electrons, which is why we don't do that. It's unnecessarily complicated. We don't care about the number, right? We can look up a number if we need to find it. What we care about here is what it causes, and we don't need the number to realize what it causes. Right, so it causes this bond to be weaker than this one. So you could compare the strengths of these bonds using this. Alright, I think I'm going to do one more topic, and this might go a little over your class time. Please just finish the video for homework in that case. It'll only be a few extra minutes. For this chapter, you're not going to have too much homework until I get back on track. Once we get into next week, really, I am going to be assigning AP Classroom videos before I go over the topic. So I want you to watch the video, try some questions the night before, then we will go over the questions afterwards. So actually, I've already talked a lot about the structure of ionic solids. All right, I have already discussed, right, actually let me oh, didn't mean to do that, sorry. Here we go. We do the reminder again. It's that alternating plus and minus and plus and minus. This causes, again, I talked about this briefly before the school year, a brittleness in this structure. This is caused by the fact that if a certain amount of physical force could shift this over, and you'd end up with positives and negatives being next to each other, which would then repel outwards. This causes ionic compounds to be brittle. But let's also talk about conductivity, right? I mentioned before that the delocalization of metallic bonds, the delocalization of electrons in metallic bonds, allow for metals to be conductive. They allow them to conduct electricity. So in order to conduct electricity, you need to have free-flowing electrons or just free-flowing charges. Ionic compounds do not conduct electricity. If you take a large chunk of salt and you jam it into an outlet, you're not going to shock yourself. However, molten ionic compounds do conduct electricity. A molten ionic compound would be when you melt this into a liquid form. In a liquid form, it loses its structure and it becomes a jumbled mess of positives and negatives floating around. Overall, just kind of canceling each other out. This allows the charged particles to be freely moving and allows for electricity to be conducted, and they can move in one direction or another, carrying that potential energy as they're introduced to a charge. So that allows for electricity to be conducted. So in that case, it does conduct electricity. In addition, a solution with an ionic compound conducts electricity because the ions dissociate when they dissolve. Ions, when they dissolve, dissociate. So you don't have sodium chloride just dissolved. You have sodium plus and Cl minus. These are also freely floating around in the water, allowing for it to conduct electricity. So water on its own does not conduct electricity. The only reason water can be an electricity hazard is because of ions in the water. And actually, I'll show you this later, but if we go into the lab and we try to run a cell, well, we won't talk about electrochemistry for a while, but if we try to set up a light bulb putting wires in water, it will not work. All right. I think I'm going to end this off here. Well, maybe I'll look through the questions really quick. Then we're going to end off. So again, conductivity of a compound. We just talked about this one. Which of the following correctly indicates whether the solid represented by the particulate model shown above conducts electricity and explains why or why not? So I just mentioned these ones do not conduct electricity because the ions cannot move freely. It needs to be able to move, right? Because the conduction of electricity is these moving in response to the electricity, creating potential energy that carries on throughout the substance, and that potential energy is then transferred through, because that's what electricity is. It's potential energy due to the movement of electrons. All right, and so actually, okay, so again, the quick reason why these are wrong: it doesn't conduct electricity, it doesn't conduct electricity. Particles being different size doesn't matter. Small space between sizes don't matter. It's all about freely moving. The particle level diagram represents the solid structure of solid Kf. Although the molar mass of KCl is greater than Kf, the density of KCl is actually less than that of Kf. Which of the following representations of the structure of KCl best helps explain this? So we can look and we can see we're looking for something similar to this. And the best explanation for this is actually that our positive ions here are bigger. Density is all about mass per volume. If the atoms are physically bigger but don't have that much more mass, then they're going to be taking up more space but not having enough mass to account for that. again, this is because you go down the periodic table, you're not adding that many more protons, right? You're increasing, if we go to the properties section, oh, sorry, if we go to the series, you're increasing the mass, you're doubling the mass, but you're also greatly increasing the volume. And you're doubling the mass of just one component, not the other component. But you're greatly increasing the distance. And now we have the energy required to dissociate an ionic solid into gaseous ions, lattice energy, is shown in the table above. On the basis of Coulomb's law, which of the following best helps explain the large difference between the lattice energies of NAF and MgF2? When we talk about lattice energy, we talk about that structure we have, the positive, negative, that is often called a lattice. And it's actually named after a lattice fence. So some of you probably have a lattice fence at home. This is what a lattice fence looks like. Right, it is, oops, yeah. This crisscrossing. So think of each of these things here as a positive or negative, positive, negative, positive, negative, filling in the gaps, forming a lattice structure. The lattice energy is the energy holding that together. So the basis of Coulomb's law, which best helps explain the difference between the lattice energies of NAF and MgF2. It's going to be the charge, right? The magnesium and sodium cations. Well, let's look. Magnesium and sodium are right next to each other on the periodic table. Their R value is just about the same, right, for the radius. The distance between them is just about the same because they're about the same size molecules, but you have twice the charge on magnesium, causing a great increase in the force of that bond. All right, with that, I think we're going to call it a day. I think I've gone just about up to the start of class with attendance. I don't know if this is going over. Have a great day, everybody. I promise I do miss being in class. I hope to see you guys soon. I would introduce you to my baby, but it is 9:44 at night. So, have a fantastic day.